Welcome to the UGC lecture series. This is the EPG Pathashala lecture series on computer science, and we are talking about the paper machine learning. In this and the next module, we will be talking about a particular type of probabilistic machine learning which is called as Bayes belief networks. So, these are the people who are responsible for the creation of this module and for developing this module. Now, let us look at the learning objectives. In this module, as I already told you, there are two modules on Bayesian belief network. In this module, we are going to explain what are Bayesian belief networks, and we are going to discuss the basics of probability of Bayesian networks, and then we are going to look at some examples to illustrate what are Bayesian belief networks. And the keywords associated with this module are Bayesian belief networks, conditional independence and joint probability distribution. Before we go further, I just want to give you a small link to what we have studied before. So, when we were talking about machine learning, we started with talking about probabilistic reasoning in general. Then we spoke about the first and simple type of probabilistic reasoning, which is naive Bayes classifier. And we said when we were talking about Bayes optimal classifier, naive Bayes classifier, then we said Bayesian belief network. So, what is the connection between these two? In this, a number of in Bayesian belief naive Bayes classifier, all the variables are assumed to be independent, conditionally independent. Here we are removing that and allowing a subset of variables to be dependent, conditionally dependent. So, this is what is the difference between naive Bayes and Bayes belief networks. Now, introduction. Let us suppose you are trying to, what is this Bayesian network? To understand that, let us take an example. Suppose you are trying to determine if a patient has inhalational anthrax, and you as a doctor observe the following symptoms. The patient has a cough, a patient has a fever, and patient has difficulty breathing. Now, you would like to determine how likely is that the patient is infected with inhalational anthrax, given that the patient has a cough, a fever and a difficulty breathing. However, given these three symptoms, we are not 100% certain that the patient has anthrax because of this. So, we are dealing with uncertainty. What is uncertainty here? Given these symptoms, we think that the patient may have inhalational anthrax, but there is no certainty. So, we are dealing with uncertainty, and this is a very important problem because we cannot give medicine for inhalational anthrax just on an uncertain diagnosis. So, with this we go to the next. So, now in the same scenario, suppose that as a doctor you order an X-ray and observe that the patient has wide mediastinum. So, this is from the X-ray you can determine this. Your belief that the patient is infected with inhalational anthrax is now much higher because of additional data that you have got by getting an X-ray done. What you have observed affected your belief that the patient is infected with anthrax. So, what you have done is you have given some symptoms, then you think that he has inhalational anthrax. This is the way doctors work. So, based on those symptoms you give you order an X-ray. From the X-ray you make an observation, and that observation has affected or increased your belief that the patient is infected with anthrax. So, this reasoning with uncertainty, a methodology that allows you to reason with uncertainty, is what is called as Bayesian networks. So, now let us discuss what is a Bayesian network. Okay. So, Bayesian networks are a network based framework obviously for representing and analyzing models involving uncertainty. We saw a typical example of uncertainty there. So, this is a framework which is used for analyzing models involving uncertainty, and they are Bayesian network, short form is BN, are different from other knowledge based system tools because uncertainty is handled in a mathematically rigorous yet efficient and simple way. So, most knowledge based system have this type of tools to handle uncertainty, but Bayesian network has the advantage or is powerful because everything is handled in a mathematically rigorous way. You can explain how you handle that, but it is at the same time efficient and simple. And Bayesian networks are different from other probability analysis tools because of the following factors. One is network representation of problem, use of Bayesian statistics, and the synergy between this. So, one is you are using a network representation for representing the problem. The second thing is you are using Bayesian statistics, and both are synergized to give you a better model. Okay. And it is a graphical model that efficiently encodes the joint probability distribution from a large set of variables. Now, this is what makes Bayesian network different. What Bayesian network does is it tries to encode the joint probability distribution between a large set of variables. So, naive Bayes is based on the assumption of conditional independence, while this graphical model or the Bayesian network is based, can consider joint probability distribution also. There is no assumption of conditional independence. So, Bayesian networks provide a tractable method for specifying dependency among variables. While naive Bayes talked about conditional independence, Bayesian networks is giving you a method for specifying dependencies among the variables through the joint probability distribution. So, why the excitement? Why suddenly we are talking about Bayesian networks, and lot of work is going on in this? What are they? Bayesian networks, as I already said, was a network based framework for representing and analyzing models involving uncertainty. So, basically networks based framework for representing as well as analyzing models of involving uncertainty through probabilistic distributions. So, what are they used for? They are used for a wide variety of applications: intelligent decision aids, data fusion, feature recognition, intelligent diagnostic aids. We saw an example there, automated free text understanding, data mining. So, there are a lot of applications where this variable dependency is important, and those applications they have used it for. Suddenly, where did it come from? It is a cross fertilization of ideas between artificial intelligence, decision analysis and the statistic communities. And why the sudden interest? Because of the development of propagation algorithms following the availability of easy to use commercial software. Before, if we had to do this type of inferencing, or this is called the propagation of the probability from variable to variable, those are called as propagation algorithms. They had to be done and coded, very difficult coding, complex coding was there. Now there is easy to use commercial software. That was one of the reasons why there is a sudden interest, and there are no growing number of creative and innovative applications that they have used Bayesian network for. This is because the naive Bayes assumption of conditional independence is too simplistic. Okay, how are they different from other knowledge representation and probabilistic analysis tools? Different from other knowledge based because uncertainty is handled, we already discussed this, in a mathematically rigorous yet efficient and simple way. And it is different from probabilistic tools because of the network representation of the problems. You do not just have a list of probabilistic equations, you have a network framework, and you are using Bayesian statistics, and there is a synergy between these two. So, this is the reason why there is a lot of excitement on Bayesian networks. Lot of papers, lot of commercial applications have used Bayesian belief networks. So, why do we need to learn about Bayesian networks? So, it combines domain expert knowledge with data. So, the expert knowledge, prior knowledge as it is called, can be combined effectively with data, and there is an efficient representation. You can represent and infer from the data. You can possibly have incremental learning, because as new and new observations come into the picture, you can change the learning, the learning changes. So, incremental learning is possible. It is possible to handle missing data, and the Bayesian network definition itself, or the way it is designed, is actually talking about causal relationship. So, it helps you to learn causal relationship. So, some of the very important machine learning issues are tackled here, like introduction, use of prior knowledge, good representation and inference, incremental learning, a very important problem in machine learning, handling missing data, again a important problem, and learning causal relationship. So, next question that all of us will ask is, what are Bayesian networks good for? What are they good for? What are the type of problems you can solve? So, just look at this example. We will discuss this in detail later on. So, let us assume that you have two causes and there is a symptom. So, this is a diagram. You can we will go into the components of Bayesian networks later, but just assume you have a diagram like this, or a networks like this, a cause. So, one of the problems you can solve using Bayesian network is, given the symptom, can you find the cause? So, that is a diagnostic problem. Okay, given the symptom, can you find the cause? You will look here that the symptom is given and you are trying to find the cause. So, it is the direction of the arrow, opposite to the direction of the arrow. Next is prediction. Given a particular cause, can you find out the symptom? Given a particular cause, you just follow through, can you find the symptom? So, this is called prediction. Next is for classification. So, given the data, what is can you find the class? That is for normally we use a argument max function to find the probability of the class given the data. Then some of the applications where this are used, again decision making. So, given a cost function, can we look at minimizing the cost. So, the decision making is also a typical application of Bayesian network. So, this Bayesian belief network is a representation and formalism that can be used for diagnosis problems, prediction problem, classification problem and decision making problems. So, some areas, for example, it can be used, it is used widely in medicine for both basically for diagnosis, also for prediction. It is used in bioinformatics for prediction, classification. It is used in computer troubleshooting for again diagnosis and decision making. It is used in stock market for decision making and prediction. It is used in speech recognition again for maybe classification, and it is used in text mining also for classification, text classification problems. So, you will see that Bayesian networks is a formalism, its formalism itself allows you to do diagnosis, prediction, classification, decision making in areas as wide as medicine, bioinformatics, computer troubleshooting, stock market, speech recognition and text classification. There are other areas also. Now, let us take an example of an application, a recommendation system. So, given user preferences, the recommendation system definition is that given user preferences, we want to suggest recommendations. So, example Amazon.com, all of you have used Amazon.com, you will see that if you search for a book, then there will be a list of recommendations to you of all other what other books users similar to yours has searched for. So, this is the recommendation that Amazon.com has been using for a long time. All of us who try to use Amazon.com to search for books or buy books know that this is the recommendation that they give. So, what does he use there? Just to understand the concept, he will look at what you have searched for, maybe your search terms, and see what are the other users who have used a similar search terms, and then find out what are the other books that particular person has also looked at, and those are recommended to you. So, that is the basic idea. Now, let us take an example, another example of movie preferences of many users. So, what you are given is, you are given the users and the movie preferences of each and every user. So, the solution is you want to model the correlation between the movie features. For example, users who like comedy often like drama also. So, how do you do this? You have a matrix, it is called the user preference matrix. So, you have users and you have the preference for the movies. So, and you have information attributes associated with the movies, and you have to find a correlation between the features of the movie. So, comedy, actor, genre, who are the actors, what is the length of the film, maybe a lot of other things, director for example. So, all these are features associated with the movies. So, you are trying to find a correlation between these features. So, users who like comedy often also like drama. So, there they are trying to correlate the features of genre. Users who like action often do not like cartoons, that way also. Users who like Robert De Niro films often like Al Pacino films. So, this is also possible. So, given, now what are we doing here? Given the user preferences, you can predict the probability that what are the new movies that a user would like to see, match the preferences. This is a very commercial product available for movie recommendation. There are books recommendation, product recommendation. So, recommendation system is a big thing in, especially in today's e-commerce market, online marketing and selling. So, now let us look at a standard or sample general product tool. Now, this is the look of a Bayesian belief network, where you have x1, x2, x3, x4, x5, x6. You have 6 variables, and we want to find the probability of this network of all the variables. So, x1, x2, x3, x4, x5, probability of everything put together. Now we are going to look at how this is defined depending on the arrow. I will explain what that means later. So, the probability of x6 depends on the probability of, so given xy, you can, the probability of x6 given x5, this can be defined. The probability of x5, you can see the arrows, given x2, x3. The probability of x4 given x1, x2. The probability of x3 given x1. The probability of x2 given x1 and the probability of x1. So, this list of probabilities or individual probabilities will give you the probability of the complete Bayesian network. So, you will see that it is a product of conditional probabilities or just a prior probability. So, here there is a dependence between the variables, that is why we have a conditional probability. So, before we go further, let us just look at some fundamentals of probabilistic fundamental, which we have already seen, but still just to make it more specific, let us say. So, first we will discuss what is a joint probability distribution. So, a joint probability distribution P of A is equal to true, B is equal to true means that the probability of A equal to true and the probability of B equal to true, that is the meaning of joint probability. Conditional independence, this is very important when we understand Bayesian networks. X and Y are conditionally independent given Z if given Y is equal to Y and Z is equal to Z, you can find probability of X, but that time that is equal to probability of X given Z for all values of X, Y, Z equivalently. If we know Z, then knowing Y does not change the prediction of X. This is a very important aspect. So, you are given that you have a variable X and you have two variables Y and Z. Now, if the variable the probability of X given Y and Z is equal to the probability of X given Y, then it means that knowing Z does not give us any extra information. In this case, knowing Y does not change the prediction. So, this is notated like this, that is X comma Y, X and Y is equal to P of X given Y and Z is equal to P of X given Z. In other words, it is independent, X and Y are independent given Z. This is conditional independence, very important property that we will be discussing again and again. The next is a Markov condition. So, given its parent P1 and P2, a random variable X, you can look at the figure, the random variable X is conditionally independent of its non-descendants. So, given the parents X and Y, the X here is conditionally independent of its non-descendants. We will come into this in for example, in this example ND1 and ND2. So, X is in no way dependent on ND1 and ND2. That means the prediction of X is not changed depending on ND1 and ND2 given the parents. Okay. So, this is what is called as conditionally independent. Now, let us look at some terminology. Okay. So, first, a Bayesian belief network describes a probability distribution over a set of random variables y1 to y2 to yn. We saw a network with Bayesian networks with 6 variables x1 to x6, and each variable yi can take a set of values, some values v of y1. For example, it could be Boolean, true or false, or it could be, for example, fever, high, low, medium, something like that. Now, the joint space of the set of variables y1 to yn is the cross product of the values of y1 into the values of y2 into the values of yn. So, joint probability distribution specifies the probability of the items in the joint space. It gives you the probability. So, for each value you will have a different probabilities. So, these are the first set. Now, a Bayesian network provides a way to describe this joint probability distribution in a compact and structured way. That is what this Bayesian network is allowing you to do. So, a set of, so what is this Bayesian network? A set of random variables makes the nodes of the network. A set of directed edges, links, we have not discussed this, or arrows connects pair of nodes. The intuitive meaning is that an arrow from x to y is that x has a direct influence on y, or there is a direct dependence. So, if there is an arrow from x to y, it means that x has a direct influence on y, or y is dependent or directly dependent on x. So, that is the meaning of the network. So, it requires that the graph is acyclic, you are not allowed any directed cycles. Each node has a conditional probability table associated with it that quantifies the effects of the parents have on that node. The parents of a node are all the nodes that have arrows pointing to it. So, two components to a Bayesian network, as I already told you, are the graph structure. This gives you the conditional independence assumptions and the numerical probability for each variable given its parents. So, due to the Markov, so again let us go back to the joint probability condition. Due to the Markov condition, we can compute the joint probability distribution over all the variables x1 to xn in the Bayesian net using the formula. So, x1 is equal to x1, you will be given a full joint distribution of all the variables with particular values. I is equal to 1 to n, probability of xi being that xi and the parents of xi. So, given the parents, you can find out the probability. You do not have to look at other things. So, when parents of xi means the values the parents of the node with respect to the graph, that is what we mean here. This is the graph structure, this is the full joint, the left hand side gives you the full joint distribution and the right hand side gives you an approximation. So, we are not taking a complete optimal classifier that we discussed in before, but we are talking about a graph structured approximation where the dependence has been specified by the parents. Now, let us take an example. Okay. Here the nodes are the domain variables and the edges are the direct causal influence. So, for example, good writer directly or reviewer mood is dependent upon the good writer and quality is also dependent on the good writer. Smart quality is also dependent on smart. So, smart and good writer determines the quality. So, these are the variables as you can see. Now, network structure encodes conditional probabilities. So, review length given the reviewer mood determines the review length as well as the good writer. So, this is what is there. Now, the conditional probability table that we were talking about, we will go discuss this in detail later, but here we are talking about the probability of Q quality is dependent upon two parents, which is W and S, that is W stands for good writer and S stands for smart. So, now you good writer and smart, we are assuming Boolean values, so can have two values, good writer can be yes or no, smart can be yes and no. So, you will have two variables coming in as parents of quality, you will have 4 entries in the conditional probability table. So, here we have given if both W and S are true, then the probability of Q given WS is 0.6 and the probability of not Q is 0.4, this is just 1 minus. And given W and not S, the probability of Q is 0.3 and not Q is 0.7. Given not of W and S, it is 0.4 and 0.6. Given both not, both false, both good writer and smart are false, then probability of quality is 0.1 and probability of not quality is 0.9. So, this is a conditional probability table associated with quality, which in turn depends on the parents. Okay. So, it is defined in this way. So, again we are taking the same example and we are talking about the semantics of this, the Bayesian network semantics. So, here you have W, S, M, Q, L and A. So, let us assume, so actually what you have is conditionally independence in the Bayesian structure. The local conditional probability tables will give you a full joint distribution over the domain. The local conditional probability tables are given by the domain expert. Okay. So, for example, suppose I want to say I want to find the probability of not a good writer, smart, okay, and M, okay. So, and quality and length and review length and mood, accepted and mood. So, we want to find out this. So, first is probability of W bar, not W negation of W, which we should have been given as input, probability of S because it does not have any parent, probability of M given W bar, probability of Q given W bar and S because those are the values that we want to consider, probability of length given mood, probability of accepted given mood and quality. So, this is a complete, so this all this is this diagram, this Bayesian network has to be designed by the expert. He knows what are the dependencies. So, it is a complete compact and natural representation of nodes and the natural parameters has to be represented. So, when you reason with in Bayesian networks, the full distribution answers any query. So, probability of event given the evidence allows combination of different types of reasoning in the same example. For example, causal, given a good writer, what would be, given that he is a good writer, what will be the probability that what will be the probability of the reviewer mode. Not accepted, please look at, you are going from I mean in the first case you are given the W parent and you are asked to find the child, probability of the child. Next you are given the child and asked to find the probability of the parent, that is called evidential, causal, evidential. Intercausal, look at this, it is not accepted and given not accepted and quality, what is the probability of reviewer mode? Now here reviewer mode is not directly connected to quality, but quality is connected to not accepted. So this is called as intercausal. So these are the three types of reasoning that you can do with this Bayes network. Now you can see that given some values, I can find out the probability of each of the other values. Now let us take another simple example. A Bayesian network is made up of a directed acyclic graph, a set of tables for each node in the graph. So here we have A there is no parent, so you have only independent probability. So P of A is equal to false is 0.6, true is 0.4. Now if you take B, the probability of B is dependent on the probability of A, and A can take on 4 values. So false, false, true, true. So given A is false and B being false, what is the probability? Given A is false and B being true, what is the probability? Given A is true and B being false, what is the probability? And given true, both, what is the probability? So this has to be given to you. Okay. Then similarly for probability of D given B and probability of C given B. So this is a set of tables for each node. For A you have a set of a table, B you have a conditional probability table, for C you have a conditional probability table, for D you have a conditional probability table. Okay. So each node in the graph is a random variable A, B, C, D. A node X is a parent of another node Y if there is an arrow from X to node Y. Example, A is a parent of B, B is a parent of C, and B is a parent of D. Informally, an arrow from node X to node Y means that X has a direct influence on Y, or A has a direct influence on B. And these are the tables that we have already discussed. Now each node X has a conditional probability distribution, and that probability depends on the parents. That quantifies the effect of the parents on the node. So that is what we have done. The parameters are the probabilities in these conditional probability tables that we talk about. So conditional probability distribution for C given B, for a given combination of values of the parents B in this example can have all false and true. The entries of P C equal to true given B and the C equal to false given B must add up to 1. So P of C true, B false plus P of C false, B false must be equal to 1. If you have a Boolean variable with k Boolean parents, this table will have 2 power k approximately to be stored. Now using a Bayesian network example, using the network in the example, suppose you want to calculate A is true, B is true, C is true, the joint probability of A is true, B is true, C is true and D is true, then P is equal to true, probability of B equal to true given A is equal to true, probability of C equal to true given B is equal to true, probability of D is equal to true given B is equal to true. For this we have to refer back to the diagram. So probability of A is equal to true is 0.4. So you write that there. Probability of B equal to true given probability of B equal to true given A is true. So that is the last one, so 0.3. So that is what you will write. Then probability of C equal to true given B is equal to true, both true, 0.1. So that is what you will write. And the final one, probability of D equal to true given that B is equal to true, so true, true, so which is 0.95. So you have the these numbers are from the conditional probability tables. So this part, that is how do you draw that, how do you write the joint probability in terms of the conditional probability is given from the graph. So if you have a parent and things, using a Bayesian network to compute this type of probability is called inference. So here we are trying to find the probability of joint probability of all the networks, some particular value. Here we are saying we want everything to be true. So in general, inference involves queries of the form probability of the query variable given the evidence. Now let us take an example. A topology of network encodes conditional independence assertions. So you have whether, cavity, toothache. Whether is independent of other variables. Toothache and catch are conditionally independent. They are not independent given cavity. So this is another new thing that we are bringing in. Given the parent, their siblings are conditionally independent. Let us take this notion of independence a little further. So let us take age and gender. Age and gender are independent. So probability, the joint probability of A comma G is probability of G into probability of A, and probability of A given G is nothing but probability of A, because G is not going to affect A, and probability of G given A is probability of G, because A does not change the probability of G. And so probability, the joint probability of A comma G is equal to probability of G comma A given A, that is P. That is how we arrived at that P of G into P of A. Now, in this particular case, age and gender. Now, let us take cancer. Cancer is independent of age and gender given smoking. So, if the parent is given, the grandparents are independent. So, that is what we have here. So, this is written as probability of C given AGS will reduce to probability of C given S, and the rest of it is independent. Here again we have an example, serum calcium and lung tumor are dependent. Okay. Serum calcium is independent of lung tumor given cancer. So, this is again the same type of example. So, age is independent of gender given smoking, that is another example, age is independent of gender. So, you have here cancer independent of age and gender given smoking, age independent of gender given smoking. So, putting it all together, you have non-descendants, you have parents and you have descendants. So, you have here probability of A, G, E, S, C, L, SC. Now, here the parents of you have P of E comma A, this is written in the E given A, probability of S given AG, probability of C given E comma S, probability of SC given C, that has not yet come into the picture, let us assume P, L given C. So, cancer is independent of age and gender given exposure to toxics and smoking, and cancer is independent of diet in this new example given exposure to toxics and smoking. So, if the parent is available, other nodes do not affect it. So, this is putting all the example together. So, the conclusion here is Bayesian networks provide a natural representation or causally induced conditional independence, and topology, the topology of the network along with the conditional probability tables gives you a compact representation of joint distribution. So, basically we are looking at a joint distribution and generally easy for domain experts to construct. Okay. So, what are the limitations of Bayesian networks? Typically require initial knowledge of many probabilities. So, quality and extent of prior knowledge will play a very important role in Bayesian networks. Prior knowledge is also the conditional probability. Significant computational cost is there, NP hard task, and unanticipated probability of an event is not taken care of. So, what is it that we have seen in this module? We have explained Bayesian belief network, we have discussed the basics of Bayesian networks, and we have illustrated Bayesian belief network using examples. So, in the next module we will go into detail of how to design and some sort of inferencing mechanism. Though in this particular paper we will not be covering the exact inference mechanisms, but we will see how inference is done. Thank you.